let's revisit our old friend, the scatter plot. We saw in the previous lessons how important it is to use plots in conjunction with descriptive statistics to spot patterns and outliers. Using both of these tools together, we get a more complete picture of what's actually going on. So far, we've been visualizing our data and looked at the distribution of values of some individual features like RM for like the average number of rooms, or RAD, the index of accessibility to highways. We can dig deeper into the relationships between these feature pairs, as well as between the features and our target value with some scatter plots. The correlation matrix that we created already hinted at the fact that there are relationships amongst the features that we can visualize. So on that note, I'd like to start this lesson off with a challenge. First, I want you to picture what the relationship would look like between the NOx and DIS features. If you recall, NOx was a measure of pollution and DIS was a measure of distance from employment centers. Picture a graph in your head and then write the 2 lines of Python code to visualize the scatter plot. I'll give you a few seconds to pause the video before I show you the solution. Ready? Here we go. So we've created a scatter plot many times before with plt, which is our matplotlib module, dot scatter. And then we have to supply 2 things, the data for the x-axis and the data for the y-axis. So on the x-axis, we're going to have our data square brackets DIS. So this is going to be our distance, which is going to be on the x-axis. And on the y-axis, we're going to have our pollution measure, which is going to be data square brackets NOx. And then finally, plt.show. So hitting Shift-Enter just gave me this error because I've come back to this notebook and I haven't run the cells above it yet. So I'm going to go to Cell, Run All, and then I'm going to wait a little bit, scroll all the way down, and here we go. Was this the relationship that you imagined in your head? A kind of downward sloping line? Let me add some labels to this graph before I give you my interpretation. So plt.xLabel, it's going to be DIS, distance from employment, and say font size 14. And then for the Y label, I'm going to copy this line, paste it in, change it to the Y label, change that to read NOx, nitric oxide pollution, and then my figure size I'm going to change as well. So I'm going to make it a bit bigger. So I'm going to say plt.figure, parentheses, fig size equals, parentheses, say maybe 9 and 6. And then I'm also going to add a title here. I'm going to say plt.title, parentheses, single quotes, DIS versus NOx, font size 14. Let me refresh this graph, see what we get. Okay, so this makes the relationship between distance from employment centers and NOx, our nitric oxide pollution, much, much more clear. What we can see here is that as distance increases, as we go more to the right of this chart here, pollution goes down. And this makes sense, right? The city center of Boston is going to be an employment center, but city centers would also have much more air pollution than in the suburbs or in the outskirts of a city. Now, one thing that might be quite interesting to add to this graph is a little bit of transparency on these data points, as well as the maybe putting down the correlation that we've calculated up here and including that in our title. So let's do that now. To calculate the correlation, I'm going to add a NOx underscore DIS core variable. Set that equal to data square brackets NOx dot core parentheses data square brackets DIS. And then what I'm going to do is in the title, I'm going to use this variable here, and I'm going to include it in my string. And I'm going to use Python's f-string notation to accomplish this. So I'm going to put an f in front of the single quote, and then I'm going to modify my string as follows. I'm going to say parentheses, correlation, and here's the key, curly braces, nox underscore dis underscore core. So this is going to grab our variable from up here. It's going to grab our correlation between distance and pollution, and it's going to insert it into our string. And that's thanks to the fact that we have the curly bracket notation outside of the variable name and this little f in front. So let me hit Shift Enter and let's see what this looks like. Voila. Now we've got a graphical representation of our data and the correlation all in one place. And the correlation is indeed negative, and it's quite high actually with 0.77. Now in terms of styling, you might say to yourself, you know what, this number is way too precise. It's difficult to read because it's got too many values after the decimal point. So why don't we round it? And we can do this with the Python round function. So I'm going to do it up here where I've actually calculated the correlation. And I'm just going to surround my correlation calculation with this Python function. So round, comma at the end, and then a value for how many decimal places I want to round it to. So I'm going to round it to 3 decimal places and close my parenthesis at the end. And if I press Shift Enter now, it should refresh and we should get something like this. We should get minus 0.769. The other thing I quite like doing with scatter plots is adding a little bit of transparency to the data points so that we can get a better feel for how dense particular areas of the chart are. So in my line of code where I'm creating my scatter plot, namely this one, I'm going to add some other keyword arguments. The transparency is set with the alpha keyword, and I'm going to set it to a value of 0.6. Let me hit Shift Enter. And we can clearly see that there's a lot more data points here than over here. I think this is a nice touch. But we can make this even more explicit by changing the size of our dots and making them a little bit larger. So if I choose something like 80, s equals 80 as a keyword argument, changing the size, then I've got slightly larger dots for my data points. Now, of course, we can continue adding keyword arguments here to style the graph as we see fit. Famously color, and there's quite a few to choose from. I'm going to go with indigo and give my scatter plot a purple makeover. Okay, so I think creating a scatter plot with matplotlib is pretty straightforward. But now let's do the same thing with the Seaborn module to mix it up a little bit. Because remember how I said that Seaborn builds upon matplotlib? Well, you're going to see in a minute how Seaborn really adds some nice little touches to these visualizations. Check this out. So I'm going to come down here, add a few more cells, and then I'm going to write the following code. I'm going to say SNS dot joint plot, so SNS being the name for our Seaborn module, and then joint plot being the function to create our scatter plot. So let's see, joint plot x equals data square brackets dis and y equals data square brackets nox. And then on the next line, I'm going to say plt.show and hit Shift Enter. And what we get is something like this. Now again, I've only specified 2 parameters in my function call here, but you can already see that there's some sort of histogram on the side, and there's some additional data being provided here in this corner. Now, if you can't read this on your screen, this is actually the Pearson correlation coefficient down to 2 decimal places, minus 0.77. I can make the chart a little larger so that it's a bit more clear by going to the arguments and providing the size argument. So I'm going to say size equals 7. Increase the size a little bit, but not too much. And now you should see the chart appear a little bit larger on your screen. But I think these histograms and the correlation coefficient, and the fact that it adds some labels for the y-axis and the x-axis automatically straight out of the box is a really, really nice touch. In terms of styling, one thing that you might notice is that the Jupyter Notebook remembers how you've styled charts previously. So if you're working in a new cell and you want a new look for the chart, you might have to reset the styling. The way to reset the styling for Seaborn is with a function called set. So sns.set parentheses will reset the styling to the default styling. So now if I press Shift Enter, I get the default parameters for this styling, and we kind of get this look right here. This set function is a good function to remember if you've ever got like a little bit of a longer notebook that we've got here, and you might have written some code up above that changes the styling of these charts, and you want to do something different, and your notebook is behaving a little bit unexpectedly. So sns.set resets the styling to default, and sns.set_style allows us to choose kind of like a template style to use for the chart. So there's a couple of templates to choose from. One of them is called white, and this template will make our chart look like so, which is kind of what we had before. But there's another template called white grid, which then adds these grid lines to the chart like so. Now, of course, there's also like dark grid and dark, and pressing Shift Tab on this function will actually show us what some of the options are. Dark grid, dark white ticks. Got a couple to choose from if we want. And they've even got some examples on how you would use them. So for example, if you wanted to use ticks, you can even provide the tick size as an additional argument. All right, so that's a little bit more detail on how you can control the aesthetics of your Seaborn chart in your notebook. But the last thing I want to mention is that there's an additional template that you can mix and match with, say, white grid or dark grid. And these templates are called contexts, if you will. So sns.set_context parentheses will allow us to put in a template here for how this chart's going to be used. For example, a context might be talk. And if I use that, then you can see that the font size is a lot larger and the dots are a little bit more clear. So this is presumably because you want to present this chart somewhere. Now there's a couple of other contexts as well. You can use notebook, which will make the chart look like this. This is a template that's quite good if you're viewing this kind of stuff on a monitor and you're not having to throw it up on a screen or like a presentation. And pressing Shift Enter on context shows us that there's a couple of other options as well. So there's paper, there's poster, and there's talk and notebook, which we've already looked at. I'm going to go with talk just to make it a little bit more readable on the video. The very last thing I want to mention on the styling front is how you can get the similar sort of transparency and the color that we have here on Matplotlib. So I want to show you how you can set that by supplying certain arguments. The color argument is pretty straightforward. So color indigo will give us a purple chart. But when it comes to the transparency, you have to supply the argument in a different way, because jointplot doesn't take an argument called alpha. That's only for Matplotlib. Instead, you have to go to the keyword arguments. So joint_KWS and then equals, and here you provide a dictionary, a Python dictionary. So that uses the curly braces notation and then a key value pair. Alpha for the key, colon, and then say 0.5 for the value. If I press Shift Enter now, we'll have the transparency applied to our data points. So I hope you find it useful to see two different ways of generating this chart with different modules. The first one, Matplotlib, and the second one being Seaborn. Now there's a really cool thing I want to show you next, and that's to do with the fact that this joint plot method is actually incredibly powerful. So let me copy this cell and paste it below. So I have 2 copies of it now. And what I'm going to do is, just for comparison, I'm going to modify how these data points are represented here. So I'm going to go with a blue color to set them apart. So I've got my blue one here, purple one here. And then what I want to do is I'm going to show you this keyword argument that I'm going to change in the quick documentation. So pressing Shift-Enter on joint plot shows us that this keyword argument, kind, is set to scatter by default. But there's other values that this can take. For example, KDE, REG, resid, and hex. So we've actually got a choice between 5 different values. Let me show you what one of them does. I'm going to go ahead and delete this argument here where we've set our alpha value. And if I press Shift-Enter, you can see that we no longer have any alpha values on our chart. But if I come in here and I change the kind to hex, so writing kind equals, and then single quotes hex, and I hit Shift-Enter, we get the following. We get a chart that looks like this. And what this chart is doing is that it's aggregating the data points that all fall in a certain area, and then it shades them in depending on how many data points there are in that particular sector. So you're aggregating the data points over like a little 2D area, and again, the shading gives us a very good idea of the density of the data points in that particular part of the plot. In other words, we're aggregating the data in a hexagonal grid. And I think this is quite a beautiful visualization, actually. And it's one that you don't tend to see that often. But it does remind me a little bit of a board game called Settlers of Catan, but maybe that's just me.